Welcome to the Deep Dive, the show where we cut through the noise and get straight to the cutting edge of technology and science. Today, we're going to push the boundaries of what you thought was possible with artificial intelligence, particularly when it needs to operate, well, in the blink of an eye. We all marvel at what AI and neural networks can do these days, recognizing faces and photos, powering autonomous vehicles, all that stuff. But here's the real challenge, the tricky part. Imagine an intelligent system that doesn't just need to be smart. It needs to react instantly, like with absolutely no perceptible delay. Think about maybe a robotic arm on a really bustling factory floor. It has to identify and sort rapidly moving objects in just milliseconds. Or maybe an autonomous vehicle detecting a sudden, completely unexpected obstacle at highway speeds. There, a fraction of a second can mean the difference between safety and, well, disaster.
Yeah, or even something like a next-generation prosthetic limb. It needs to interpret muscle signals and respond with fluid, natural movement, all in real time.
Exactly. And for all its brilliance, conventional AI, the kind that often relies on these powerful but, large data centers, it frequently struggles. It hits a wall with the sheer computational demands for truly real-time performance in these mission-critical scenarios.
There's a fundamental bottleneck there. It prevents the AI from truly living and reacting in the moment, right at the edge, where the decisions actually have to be made.
So today we're diving into a fascinating and I think incredibly clever solution that marries biological inspiration with some truly ingenious hardware engineering. We're going to unpack a groundbreaking architecture that uses something called the Neural Engineering Framework, or NES.
What, the NEF? It's a method for building these large-scale, kind of brain-like models.
And it implements it on specialized hardware known as Field Programmable Gate Arrays, FPGAs. The goal here: to achieve massively parallel real-time pattern recognition, but with remarkable efficiency. Our mission in this deep dive is to understand precisely how the system takes raw data. In this case, they used handwritten digits, the classic MNIST set, and processes it at speeds that might just, well, blow your mind, all while being incredibly resource efficient. So you're going to discover how a few ingenious design choices, really meticulously informed by hardware constraints, lead to surprisingly powerful results.
Yeah, it offers you a shortcut, really, to being well-informed about the cutting edge of this neuromorphic hardware space.
Okay, let's get started on this journey. Okay, let's unpack this core challenge first. We all know neural networks are incredibly powerful tools. Pattern recognition, classification, even prediction. They're the engine behind so much AI we interact with. But what is it about that need for real-time performance, that absolute instantaneous reaction that makes conventional neural networks so difficult to implement effectively, especially, out there at the edge? Where does this fundamental bottleneck actually appear?
That's a crucial starting point. What's fascinating here is that while conventional neural networks are incredibly effective, yeah, they are inherently computationally demanding. They're just heavy. They're designed more for software execution on general-purpose processors, think CPUs or GPUs, which, okay, they're powerful, but they operate in a largely sequential or maybe batch processing kind of manner.
Step by step, or in big chunks.
Exactly. And those architectures aren't ideally suited for the highly parallel, instantaneous processing required for truly real-time control. It's a fundamental mismatch, really. A mismatch between how these networks are typically run and the demands of immediacy. Imagine trying to have a fluid, natural conversation if every single word had to be processed through, I don't know, a server farm miles away.
Yeah, the delay, even a tiny one, would just make it impossible, awkward at best.
Totally. And this fundamental challenge of trying to balance the immense complexity of these networks with the need for immediate, high-speed responses often prohibits their use in critical applications. Things like interactive robotic systems, autonomous vehicle control, advanced prosthetics. Anywhere even a millisecond delay can have pretty significant consequences.
Okay, so if we can't just throw more processing power at the problem, or maybe we can, but it's impractical for edge devices, and conventional architectures are struggling to keep up with this demand for true immediacy. What does this all mean for someone wanting to put advanced AI into, say, a tiny drone, or a compact smart device, or even a medical implant that absolutely cannot afford to carry a supercomputer around or rely on, flaky cloud connectivity?
Well, it means we need a fundamentally different approach.
A different approach, right. We can't simply optimize the existing paradigms. We probably need to rethink the architecture from the ground up. Maybe look for inspiration somewhere else.
Exactly. And this raises an important question. What if we don't try to force biological computation, which is inherently parallel, incredibly energy efficient, onto traditional sequential architectures that are, frankly, optimized for different tasks? What if, instead, we build hardware inspired by biology itself, by the brain's incredible efficiency and parallelism?
Ah, so that's the core of neuromorphic engineering then.
That's precisely it. It's about drawing lessons from the brain's unique structure and function to design entirely new computing systems. Systems that are intrinsically suited for real-time, low-power, and highly parallel cognitive tasks.
And that's where this neural engineering framework, the NEF, comes in. It sounds quite fancy, maybe a bit academic, a framework for engineering neural networks. But what exactly is it, and what makes it so powerful for this specific challenge? The real-time processing and efficient hardware implementation.
Right, the NEF. It was first introduced back in 2003 by Chris Eliasmith and Charles Anderson. And it is, well, sophisticated, yes, but also remarkably elegant as a framework. Its power really lies in its ability to systematically build large cognitive systems by combining smaller, well-defined neural subnetworks. It simplifies the design process for complex neural networks.
How does it simplify it?
By offering a standard three-layer neural structure, it provides this principled approach for synthesizing these systems based on how neurons actually represent and process information.
A three-layer structure. Okay, so that sounds familiar. Like a classic feed-forward neural network you might learn about in, say, a basic machine learning course. Input, hidden, output layer.
Exactly like that structure, yes. It consists of an input layer, which receives the initial stimulus in our case. That would be the pixel data from a handwritten digit. Then there's a hidden layer. This is the computational powerhouse, really. It's made up of a large number of nonlinear neurons, and they do the heavy lifting of the network's processing. And finally, an output layer, typically composed of linear neurons, and this layer delivers the network's final answer, which digit it thinks it recognized.
Okay.
The brilliance of NEF lies in its well-defined mathematical processes. It specifies exactly how information flows and gets transformed across these layers, which allows for precise control over the network's function. So the NEF performs three core tasks to calculate a desired function. Understanding these is really key to grasping its efficiency. First, there's encoding.
Encoding, got it.
The input stimulus is encoded into the hidden layer neurons using a set of fixed random weights. Now, each individual neuron, crucially, has a distinct tuning curve.
A tuning curve, like how it responds to different inputs.
Exactly. Imagine a radio dial. Each neuron is effectively tuned to respond most strongly to a specific range, or you could say frequency, of input. So one neuron might light up for a thick vertical line in a digit, while another might react most intensely to a thin diagonal stroke. This nonlinear function, combined with those random weights coming from the input, ensures each neuron has a unique perspective on the input. It creates this diverse and really rich representation in the hidden layer. Second core task, decoding. The activity of these hidden neurons, basically their firing rates, how strongly they're responding, is then decoded. The output of each hidden neuron is multiplied by something called a decoding weight. Now, these critical weights aren't found through slow, iterative trial and error like in many other networks.
How are they found then? That sounds important.
They are found by analytically calculating the Moore-Penrose pseudo-inverse of the hidden layer's activity.
Okay, you mentioned the Moore-Penrose pseudo-inverse for decoding. That sounds mathematically intense, maybe a bit scary. But what does it truly mean for the practical learning aspect of this network, especially when you compare it to the iterative training we always hear about, backpropagation and all that? This feels like a really significant differentiator.
It absolutely is one of NEF's core differentiators, and it simplifies the whole process dramatically. You're right, traditional neural networks, especially deep learning models, often spend hours, sometimes even days, iteratively adjusting weights using algorithms like gradient descent, backpropagation.
Yeah, the really compute-heavy stuff.
Exactly. But the Moore-Penrose pseudo-inverse provides a direct, elegant mathematical solution. It allows you to calculate the optimal decoding weights in a single non-iterative step. Bang, done. For a given network configuration, you just compute those weights once, and that's it. No lengthy training phase, no gradual convergence over millions of examples. It's an immediate analytical solution.
Wow, so it completely skips that long training cycle.
Pretty much.
Yeah.
This not only saves immense computational resources, obviously, by avoiding those extended training cycles, but it also drastically reduces the time to deploy and, importantly, reconfigure the system for new tasks. This immediate analytical weight determination is paramount for real-time applications where you simply cannot afford extended training phases or constant recalibration in the field. And third, the final core task is averaging. The final output of the system is simply the linear sum of these weighted firing rates from the output layer neurons. This last step is quite straightforward. It just combines the decoded information into the final decision.
Okay, so encode with random weights and tuning curves, decode analytically using the pseudo-inverse, and then just sum it up.
That's the essence of it, and the elegance and power of the NEF were really demonstrated by its use in constructing
Wait,
Spotman.
what?
It's a large-scale brain model. It's capable of solving a really wide range of cognitive tasks, remembering lists, pattern matching, even basic reasoning in a remarkably human-like way. That truly underscores the NEF's flexibility and its capacity for creating complex, biologically plausible, and importantly, effective systems.
Okay, so we have this powerful NEF concept. It's biologically inspired, it's capable of sophisticated cognitive tasks, and crucially, you can analytically solve for its decoding weights, no long training needed. That's huge. But how do we take this framework and make it run in real time on actual hardware? How do we tackle that computational bottleneck we started with? The paper's authors developed a specific architecture for field programmable gate arrays, FPGAs. Why FPGAs specifically, and what did they choose as their proof of concept to show this system actually works in practice?
Right, FPGAs are really the perfect canvas for this kind of work. They represent this unique blend of hardware flexibility and performance. Unlike a fixed processor like a CPU or a GPU, FPGAs allow for custom reconfigurable hardware logic.
Reconfigurable, so you can change the circuits.
Exactly. You can literally design and effectively rewire the digital circuits on an FPGA to precisely match the needs of your neural network. You can create highly specialized, massively parallel neural circuits tailored to the task. This level of customization is precisely what neuromorphic engineering needs to mimic that biological efficiency.
Makes sense. And the proof of concept.
For their proof of concept, they developed a handwritten digit recognition system, leveraging the famous MNIST database.
Ah, MNIST, the standard benchmark.
Precisely. It's a well-understood, very well-characterized data set with tens of thousands of examples. That makes it an excellent and robust benchmark for verifying and validating their approach against a whole multitude of existing systems. It allows for clear apples-to-apples comparisons of both accuracy and efficiency. Now, the core of their hardware implementation hinges on two truly ingenious innovations. First, the design of a compact digital neural core, and second, a clever technique called time multiplexing. These two elements work together in concert to maximize efficiency and scale, really pushing the limits of what's possible on limited hardware resources.
Time multiplexing, you mentioned that. It sounds like something from an old phone system, maybe,
Yeah.
where different conversations share the same physical line by taking turns. How does that concept apply to individual neurons and a whole neural network in hardware?
That's actually a perfect analogy, and it's quite similar in principle. Time multiplexing leverages the extremely high clock speed of modern digital circuits.
Yeah.
In this specific case, the FPGA was running at 266 megahertz. So instead of building a separate dedicated physical circuit for every single neuron in your network, which would consume an enormous amount of hardware real estate and power, they use a single physical neuron circuit to simulate many virtual neurons in sequence. Think of it like a highly efficient assembly line. One physical worker, operating very, very quickly, performs the task for multiple products one after another, instead of needing a separate worker for each product simultaneously.
So essentially, one physical circuit is doing the work of, say, 64, maybe even more, virtual neurons just by rapidly taking turns processing the data for each one.
That sounds incredibly efficient, like a massive multiplier for your available hardware resources.
Precisely. This brilliant technique allows them to simulate up to 256,000 virtual neurons using a much, much smaller physical footprint than would otherwise be possible. Each of these virtual neurons gets updated almost every millisecond, which, for many systems like interactive robotics where delays of hundreds of milliseconds are noticeable, is generally more than acceptable for real-time control requirements.
Wow.
This is how you achieve these large-scale networks with limited physical hardware resources on an FPGA. However, it's important to note the inherent limitations here. This time multiplexing approach is constrained by the size and, crucially, the speed of the on-chip memory, specifically SRAM.
Why the memory constraint? Well, for truly real-time simulation, new values like the decoding weights for the current virtual neuron or its internal state variables need to be available from memory every single clock cycle, instantly. The current design keeps it simple and incredibly efficient, but relying solely on that fast on-chip SRAM. But for even larger and more complex networks, needing many more virtual neurons using off-chip memory, like DRAM, would be a necessary future consideration.
But that would add complexity, right? Latency.
Absolutely. That would introduce challenges related to memory bandwidth, getting data on and off chip quickly enough, and increased architectural complexity. Those are often performance bottlenecks in themselves. So they stuck with on-chip for this design to maximize speed and simplicity.
Okay, the paper describes a clear, well-defined system layout, a logical topology from start to finish. Can you maybe walk us through how these clever components fit together? From the initial pixel input all the way to the final digit recognition output.
Certainly. The system is logically organized into those three main layers we discussed, mirroring the NEF structure. First, you have the input layer, which they call the encoder. This layer is responsible for taking the raw, incoming pixel data from the handwritten digit image and preparing it for processing by the hidden layer.
Okay, the encoder, got it.
This encoded data then feeds into the hidden layer, which, as we said, is the network's computational powerhouse. In this specific implementation, the hidden layer comprises 128 identical neural cores.
128 cores.
And each core contains 64 virtual neurons. So doing the math, that totals 8,000 hidden neurons.
8,000 hidden neurons. Okay, that's a decent size.
Yeah. And finally, you have an output layer with just 10 linear neurons, one dedicated to each possible digit, 0 through 9. And crucially, both the encoder, the input stage, and the hidden layer are implemented using that ingenious time multiplexing approach we just discussed. That maximizes the number of virtual neurons they can simulate with limited physical hardware.
Right, now let's really dive deep. Let's get into the specific design choices and these clever optimizations that make this architecture so incredibly efficient. The authors made some really intriguing innovations right at the input layer, didn't they? Where the raw data first comes in. They started by taking the grayscale MNIST digits, which normally have, 256 shades of gray, and converting them to just black and white. Binary pixels, 0 or 1. Now, my intuition says going from detailed grayscale to just simple black and white, you'd be throwing away a lot of valuable information. That seems like a really restrictive choice for something like digit recognition, doesn't it? Why would they intentionally make that trade-off?
It's a really textbook example of hardware-driven design, prioritizing efficiency over what you might perceive as the ideal input representation. Think about it. Each grayscale pixel typically uses 8 bits of data. Any operation involving that pixel, like multiplying it by a weight in the first layer, requires an 8-bit multiplier.
Okay, yeah.
And these multipliers are incredibly resource-intensive on an FPGA. They consume a lot of logic gates, they take up physical area on the chip, and they draw significant power. Now, if you convert that pixel to a simple binary value, just 0 or 1, that complex multiplication essentially vanishes. Multiplying by 0 is trivial. Multiplying by 1 just passes the value through. It often becomes just a simple multiplexer operation or maybe a conditional accumulation. It drastically simplifies the circuit.
Ah, I see. Much simpler logic.
Massively simpler. The cost saving in hardware resources, logic gates, chip area, power consumption is immense. And here's the kicker, the really surprising part. For this specific task, handwritten digit recognition with MNIST, this seemingly drastic conversion resulted in only a small, statistically significant increase in error. About 0.6%.
Only 0.6% worse. That's tiny.
Exactly.
Yeah.
That minimal performance hit is a tiny price to pay for the massive savings in hardware. It makes the system much more compact, much more energy efficient, and ultimately more affordable for deployment in edge devices where resources are always at a premium.
That's a fantastic example of a smart engineering trade-off. Optimize for the hardware constraints and accept a minor quantifiable accuracy reduction. Brilliant. But what about the millions of random weights needed to connect that input layer, the 784 pixels, to the, 8,000 hidden layer neurons? Storing all of those would still require a massive amount of memory, wouldn't it? How did they handle those efficiently?
Right, that's another ingenious optimization to tackle exactly that memory challenge.
Yeah.
For those thousands upon thousands of random weights, connecting the input layer to the hidden layer, instead of storing them all in memory, using a huge lookup table.
Which would need memory that scales linearly with the number of connections, right? So it gets big fast.
Precisely. It would require significant memory that scales linearly with both the input size and the hidden layer size. Instead, they generate these weights on the fly, using linear feedback shift registers, or LFSRs.
LFSRs, okay, what are those?
Think of an LFSR as a clever little digital machine. It spits out a sequence of seemingly random numbers based on a tiny initial seed value. So instead of storing millions of pre-calculated weights in precious, finite, on-chip memory,
You just store the little seed number.
exactly, you just store the small initial seed, and the LFSR circuit generates the necessary weights as needed right when the computation requires them. It acts like a deterministic random number generator.
Generating random numbers on the fly rather than storing them in a huge table. Wow, that sounds like another monumental memory saver right there. You're not just reading values from memory, you're actively creating them dynamically. That must free up a ton of space.
Indeed, it drastically reduces memory usage. Only the initial seeds for the LFSRs need to be stored, not the millions of individual weight values themselves. And they even went a step further. They optimized these LFSRs to produce more balanced random weights. A regular, simple LFSR can sometimes produce unbalanced outputs, meaning some generated numbers might appear much more frequently than others.
Why is that a problem?
In a neural network context, this can mean some neurons might consistently receive very high activation signals, or maybe always very low ones. They could effectively get stuck in an always-on or always-off state, becoming saturated or inactive.
Ah, so they don't contribute properly.
Right. So by using multiple small LFSRs and carefully combining their outputs, they ensure a much more uniform distribution of weights. This prevents neurons from getting stuck and significantly improves the classifier's overall performance and robustness.
That attention to detail is truly remarkable. It's not just about saving memory, but making sure the method used works well too. But let's talk about sheer processing speed again, back at that input layer. You've got 784 pixels, each potentially multiplied by a weight, and then summed up for each of the 8,000 hidden neurons. Doing that sum of 784 weighted pixels in just a few nanoseconds, which is what a single clock cycle at 266 megahertz would demand, that still sounds almost impossible. How did they achieve that kind of speed and manage the timing constraints?
Yeah, that's where pipelining comes in. It's a fundamental technique in hardware design, much like that efficient assembly line analogy we used earlier. A naive approach might try to sum all 784 weighted pixels simultaneously in one go. That would require potentially 784 adders working in parallel, creating a huge combinational logic path, which means a very long delay, probably too long for a single clock cycle.
Right, the signal wouldn't get through in time.
Exactly. So instead, they broke down this complex summing operation into a sequence across 4 clock cycles. Each cycle processes a more manageable chunk of 196 pixels. Imagine splitting the work across 4 stations or clock cycles on the assembly line. Station 1 handles pixels 196, Station 2 handles 197, 392, and so on.
Okay, breaking it down.
This not only mitigates the critical timing requirements by spreading the work out over time, but it also significantly reduces the total number of physical adders needed. You don't need 784 adders anymore, maybe just 196, reused over 4 cycles. The entire system then employs a 13-stage pipeline to keep everything flowing efficiently. This means that while a single virtual neuron's full computation might take, say, those 4 cycles for the input sum plus other steps, different parts of the computation for different virtual neurons are always happening concurrently in different pipeline stages.
Ah, so the pipeline is always full, always working, like a real assembly line.
Precisely. It keeps the entire assembly line full and operating at maximum throughput, even though individual tasks take multiple cycles.
Okay, let's move on to the hidden layer. This is where the bulk of the thinking happens, right? Where those complex patterns are truly deciphered. You mentioned earlier that the system uses 8,000 hidden neurons, but they're built from these compact neural cores. How do they manage to get such a large number of neurons from these cores without consuming an exorbitant amount of physical hardware resources?
Yeah, this is where the modularity and the inherent scalability of their NEF-based architecture really shine. Each neural core is designed as a standard self-contained building block. Each core consists of 64 virtual neurons, and it's capable of performing all the necessary nonlinear computations for those neurons, calculating their firing rates based on the inputs they receive.
So a standard block of 64.
Exactly. And the beauty of this approach is that you can easily combine multiple identical neural cores together to build a larger hidden layer. It's like using Lego bricks. In the system, for example, they used 128 such cores.
Okay, 128 cores times 64 virtual neurons per core. Wow, that gives you the 8,000 total hidden neurons, I see.
Exactly. 128 multiplied by 64.
So it's like a modular system then. You can just stamp out more identical cores to expand the network to whatever size you need. And even though the cores themselves are physically identical circuits, the virtual neurons within them get different unique inputs because of those random weights earlier. That diversity seems absolutely key for effective pattern processing.
Precisely. You've hit the nail on the head. Even with physically identical neurons within each core, those random weights generated by the LFSRs in the encoder ensure that each virtual neuron effectively receives a distinct, unique projection of the input image. This random projection, combined with the distinct nonlinear tuning curves of the individual neurons, makes the entire system incredibly effective for processing and recognizing different patterns. It prevents any redundancy, despite the identical physical architecture of the cores.
So every virtual neuron still has its own view.
Exactly. It ensures that each virtual neuron contributes meaningfully to the overall representation of the input pattern. And this modularity is absolutely crucial for scalability. You can make the network bigger without requiring a complete redesign of the core logic for every different network size. Just add more cores.
Okay, let's zoom in even further now, right down to the physical neuron design itself within those cores. Each virtual neuron, when its turn comes in the time multiplexing sequence, has to compute its output, its firing rate. And then you said it has to multiply that rate by 10 different decoding weights, one for each of the 10 output layer neurons, representing the 10 digits 0 to 9. Now, that sounds like a lot of multiplication operations for a single neuron's time slot. 10 multiplications, which usually means a lot of dedicated, resource-heavy hardware, right? Multipliers are expensive on FPGAs. How did they optimize that part to keep the hardware costs down?
This is yet another really clever optimization that directly leverages that time multiplexing approach we keep going back to. Remember, the time slot allocated for processing a single virtual neuron is fixed at 4 clock cycles in their design.
4 cycles per neuron. Okay.
So they brilliantly distributed these 10 multiplication operations across those available 4 cycles. Instead of needing 10 separate dedicated multipliers for each virtual neuron, which, as you say, would be a significant hardware cost and potentially a timing bottleneck, they implemented it with just 3 identical 9-bit multipliers.
Only 3 multipliers instead of 10? How does that work?
Each of those 3 multipliers works on a subset of the decoding weights in sequence over those 4 clock cycles. For example, maybe one multiplier computes the neuron's firing rate in the first cycle, then uses the remaining 3 cycles to multiply that rate by, say, 2 or 3 of the decoding weights each cycle. The other 2 multipliers handle the remaining weights in parallel over the 4 cycles. It schedules work across the available hardware and time slots.
That's a huge saving in hardware resources. But maybe for our listeners, can you put that into perspective? What does it truly mean in practical terms to go from needing potentially 10 multipliers down to just 3 shared ones? What kind of impact does that have on the overall design and its potential applications?
Oh, it's an enormous impact. Multipliers are notoriously resource hogs on FPGAs. They consume a lot of logic gates, they take up significant physical area on the silicon chip, and they demand more power than simpler logic like adders or registers. Reducing that count from potentially 10 individual multipliers per virtual neuron down to just 3 shared ones frees up a vast amount of hardware real estate and power budget.
Okay, so what can you do with those freed up resources?
Well, it means you can either fit a much larger network onto a smaller, cheaper, and lower power FPGA chip. Or, as they demonstrated in their performance analysis, you could instantiate multiple of these time multiplex layers or even entire systems in parallel on a single, reasonably sized FPGA.
So it directly enables that massive parallelism and scalability you mentioned earlier.
Exactly. This directly pushes the total processing capability into the realm of millions of operations per second, potentially. Wow. It fundamentally translates to lower cost, lower power consumption, and greater scalability, all critical factors for deploying sophisticated AI in compact, energy-constrained edge devices. Things like robotics, smart sensors, wearables.
Right. It's not about doing everything at once in parallel necessarily, but doing it cleverly sequenced at the right time with minimal physical hardware, making the most of the speed.
That's the essence of efficient hardware design, yes.
Yeah.
And finally, we arrive at the output layer. The design here is surprisingly straightforward, actually, and incredibly effective. It really reflects the NES core principles of using simplicity where possible, especially after the complex processing in the hidden layer. It consists of just 10 neurons, as we said, one for each digit from 0 to 9. These neurons are simple linear units. They just accumulate the weighted firing rates they receive from all 8,000 hidden neurons over the course of the processing cycle for one input image.
So, after all that complex processing in the hidden layer, all these clever time multiplexing tricks and optimizations, the final step is just adding up the results. And then it just picks the biggest one. The output neuron with the highest accumulated value indicates the most likely digit.
Yes, precisely that. Once all the 8,000 hidden neurons have been processed for a given input digit, and their weighted outputs have been accumulated by the 10 output neurons, the system simply identifies the output neuron with the maximum accumulated value. Its index, from 0 to 9, is then sent out as the system's final result, signifying the most likely input digit. After that decision is made, the accumulated values of all 10 output neurons are immediately cleared, reset to 0, ready to start accumulating for the next incoming digit image without any residual state carrying over.
Nice and clean.
Very clean. This elegant simplicity ensures both speed, because it's just a comparison at the end, and minimal hardware for the final decision-making step, avoiding any unnecessary complexity right at the finish line.
Okay, all these optimizations sound incredibly clever in theory. It's a testament to brilliant hardware design and a really deep understanding of the NEF framework. But the real test, of course, is always the real-world performance. How did this system actually perform when they put it to the test against the famous MNIST database? What were the numbers?
The results are quite compelling, especially, as you say, when you consider the remarkable resource efficiency they achieved. The system achieved a recognition rate of 96.55% for handwritten digits directly from the MSN database. That's a very respectable score, especially for a hardware-constrained system designed for efficiency.
96.55%. Okay, not state-of-the-art, absolute best, but very good.
Very good, exactly. And when combined with the full Opium algorithm, that's their online pseudo-inverse update method for learning, though run offline in this main test, it achieved an even lower error rate of 3.45%. So the potential for accuracy is quite high within this framework. Now, regarding speed, which was a primary goal, running at that high clock frequency of 266 millihertz with 8,000 hidden neurons, and each neuron having that time slot of 4 clock cycles for its processing. The total processing time for one input digit image from pixels in to decision out is approximately 120 microseconds.
120 microseconds. Wow. Okay, let me process that. That's 0.12 milliseconds. That means it can process about, what, over 8,000 digit recognitions per second. Is that right?
That's correct. Roughly 8,300 digits per second.
It's almost unbelievably fast. Faster than a single blink of an eye for each individual decision. That's truly what you mean by real-time performance.
Absolutely. And here's another critical point that really speaks to its incredible efficiency. Because this entire system, as implemented on a mid-range Altera Cyclone V FPGA, used less than 6% of the FPGA's total hardware logic resources.
Only 6%, excluding the RAM, you said.
Excluding the on-chip RAM blocks, yes.
Yeah.
Just the logic fabric. Because it used such a tiny fraction of the available logic, it means that multiple time multiplexed layers or even several complete recognition systems like this one could easily be instantiated in parallel on the same single chip.
Ah, so you could run maybe 10 of these in parallel on one FPGA.
Potentially, yes. Or even more, depending on the specific FPGA and RAM constraints. This makes it entirely practical to scale the system to process millions of digit recognitions per second just by replicating the efficient core design.
Millions.
This isn't just fast, it's scalable at a fundamentally efficient level. That opens doors for applications needing immense throughput, but in a compact, low-power form factor.
Right. That scalability, combined with the incredibly low resource usage, is truly mind-boggling. It paints a very different picture from giant GPU clusters. Now, earlier, we talked about some of those key design choices made explicitly to save hardware, like going from grayscale to binary inputs, using simpler rate neurons instead of the more mathematically complex TON neurons, and employing fixed point numbers for weights and activations instead of floating point. These were deliberate trade-offs. What did the detailed analysis in the paper show about the real-world impact of these specific choices on performance? Did those trade-offs ultimately pay off when they measured them carefully?
Yes, they conducted rigorous tests to quantify these very trade-offs, comparing different configurations side by side to really understand the cost-benefit analysis. First, for binary versus grayscale input. As we discussed, switching from detailed 8-bit grayscale to simple binary inputs resulted in that small but statistically significant increase in error of around 0.6%. A measurable hit, but tiny.
Right, the 0.6% hit for massive hardware savings.
Exactly. The performance hit was quantified and deemed an acceptable, even strategic trade-off for the immense resource benefit replacing complex multipliers with simpler logic. Second, regarding rate neurons versus TAN neurons, changing from the more complex, smooth TAN activation function to simpler rate neurons, which essentially output a rectified linear unit, RaLU-like response, common in modern deep learning too, that increased errors by approximately 0.19%.
Even smaller. Less than 0.2%.
Even smaller. And interestingly, this difference was not strongly significant statistically, meaning the simpler neuron model offered nearly identical performance for this specific task, making it another smart choice for hardware simplification. And then this is perhaps another aha moment, the real game changer they found. Fixed point versus floating point decoding weights. This is about the precision used for those crucial weights connecting the hidden layer to the output layer. Using highly simplified 6-bit fixed point output weights instead of the standard, computationally much more demanding 64-bit floating point weights resulted in, wait for it, no significant loss in performance.
No significant loss. Going from 64 bits down to just 6 bits. That's incredible.
Incredible, right? The statistical analysis showed that the distribution of the mean of the error difference was entirely within the region of practical equivalence. For all intents and purposes, the accuracy was the same for this task.
That last one is huge. It means you can simplify the underlying hardware dramatically, the multipliers, the memory buses, the storage, and save a ton of memory, going from a 64-bit representation down to just 6 bits, without sacrificing accuracy, at least for this specific pattern recognition task.
No.
That's a true game changer for hardware implementation where every single bit of memory and every logic gate counts, especially for low-power edge devices. It really underscores their whole hardware-driven design philosophy, doesn't it?
Precisely. It allows for much more compact, much more power-efficient, and potentially faster designs because you're moving less data around, all without compromising the output quality. It demonstrates that often, full precision, like 64-bit floating point, simply isn't necessary for achieving high performance in specific AI applications on hardware. You can get away with much less. They also, as you'd expect, rigorously investigated the effect of the hidden layer size on performance. How many neurons do you actually need? And as expected, increasing the number of neurons in the hidden layer, say from 1,000 up to 16,000, generally decreased the error rate. It showed that more neurons can indeed capture more complex patterns and relationships in the data.
Makes sense. More capacity.
Right. For instance, increasing from just 1,000 neurons to the 8,000 they settled on dropped the error rate significantly, from around 14.5% down to a much more respectable 5.01%. That's a big jump. However, they observed diminishing returns as the network grew even larger. Going from 8,000 neurons up to 16,000 only dropped the error rate further to 4.33%, a smaller improvement for doubling the neurons.
Okay, so diminishing returns set in. There's a sweet spot where you get most of the accuracy benefit without over-investing in resources that yield only marginal improvements later on.
Exactly that. They ultimately chose 8,000 neurons for the hidden layer in their final implementation because it offered the best practical trade-off between achieving the desired level of accuracy and effectively managing the memory usage. Because, while the hardware cost of adding more virtual hidden neurons itself is almost negligible due to the magic of time multiplexing, the memory required to store the crucial decoding weight scales linearly with the hidden layer size.
Ah, right. Each hidden neuron needs its own set of decoding weights for the output layer.
Exactly. So that memory requirement quickly becomes the primary bottleneck for building much, much larger networks on a constrained hardware platform. This reinforced their decision to find that optimal balance point between performance and the tangible hardware constraints, particularly memory.
Okay, this all sounds incredibly impressive. They've pushed the boundaries of real-time processing and efficiency, particularly in a resource-constrained environment like an FPGA. But how does this neuromorphic NEF system actually stack up against other cutting-edge solutions out there? Both the conventional AI approaches and maybe other bio-inspired or neuromorphic systems. Where does it really fit in the current landscape of AI hardware?
Yeah, that's a crucial question for understanding its niche and its real strengths. Let's start with what many people are familiar with, deep neural networks, DNNs, the kind that dominate many AI benchmarks today. Modern DNNs, often trained with computationally intensive backpropagation algorithms, usually on powerful GPUs, they achieve incredibly high accuracy, sometimes near human or even reported as outperforming human accuracy on datasets like Emming and Nest.
Okay.
They are heavily optimized through architecture design and extensive training for the single goal of achieving the absolute lowest error rate possible, often at a significant computational cost and power budget.
So generally speaking, DNNs are more accurate, sometimes significantly more accurate than this NEF system on a benchmark like MNIST, right? In terms of just the raw error percentage.
Generally, yes. In terms of that raw absolute accuracy on well-defined static benchmarks like MNIST, DNNs often win. The key reason is that DNNs use learned weights throughout all their layers. Every connection is typically trained. And they often include specialized feature extraction layers, like convolutional layers, that are meticulously designed or learned over vast data sets to cluster and extract the most salient features from the data automatically.
Right, they learn the important features first.
Exactly. Our NIMF approach, by contrast, uses those random weights in its input to hidden layer generated on the fly by LFSRs. This saves significant memory compared to storing all those learned weights, especially for the first layer, which can be huge. It's also inherently featureless in its core NEF design, meaning it doesn't require complex, hand-engineered, or pre-trained feature extraction layers that need to be carefully tailored to specific types of data.
So it's more general purpose, in a way, easier to adapt.
Potentially, yes. This makes it more easily adaptable to different kinds of input data without needing to completely redesign those complex feature extraction components, which can be a significant advantage in terms of flexibility and development time for new applications. So it's a clear trade-off. You're balancing that ultimate hyper-optimized accuracy of a DNN against the NEF system's adaptability, its architectural simplicity, and its far superior hardware efficiency profile. Less memory, less logic, faster analytical training. Now, if we look at conventional artificial neural network hardware that's maybe more DSP-driven, specifically designed to accelerate traditional ANNs, but perhaps not neuromorphic, we see some interesting comparisons there too. For example, one recent work they cited achieved a very impressive 0.54% error rate on MIDAST, so much lower error than the NEF system. And it had a processing speed of about 8 microseconds per digit.
Wow, 8 microseconds. That's roughly 15 times faster than the EF system's 120 microseconds, and much more accurate, too. That sounds like a clear winner on paper, doesn't it?
It does, on paper, if you only look at speed and accuracy. But there's usually a catch with that kind of performance, isn't there? Especially when we're talking about resource efficiency and cost.
Ah, okay. What's the catch here?
The catch is, as you might guess, the hardware cost. That system's hardware footprint was astronomical. It required 3,599 dedicated digital signal processors, or DSPs, on the FPGA.
3,500 DSPs. Compare that to...
Compare that to our NNF system's mere 3 9-bit multipliers used for the decoding step. It's orders of magnitude difference in specialized hardware blocks. That DSP-heavy system also consumed 2.4 million bits of on-chip RAM and used over 500,000 logic gates, vastly more resources than our NF approach used for its 96.5% accuracy and 120 microsecond speed.
Okay, so that's not something you'd put in a cheap drone.
Absolutely not. Those are resources typically only available on extremely high-end, very expensive FPGAs, or even custom-designed ASIC chips, far beyond the scope of a compact, affordable edge device. It fundamentally highlights our system's focus, achieving excellent real-time performance with exceptional efficiency and scalability, rather than just brute forcing the problem with immense costly hardware resources. It's a completely different design philosophy and target application space. And then we have other neuromorphic systems. These also draw inspiration from biology, like the NEF system, but they might have different design philosophies, maybe targeting spiking neurons or different computational models. Consider IBM's True North chip. It's a well-known, general-purpose neuromorphic system with a vast number of neurosynaptic cores. Very impressive architecture. But when they configured it specifically for MNIST digit recognition, the reported result was an 8.06% error rate. That's actually higher, so less accurate, than our NEF system's 3.45% with Opium.
Higher error. What about speed?
More strikingly, it was significantly slower for this task, about 167 times slower, needing 20 milliseconds per digit compared to our system's 120 microseconds. It also required significantly more memory resources.
Interesting. So True North is maybe more general, but less optimized for this specific pattern recognition task.
That seems fair to say based on these results. While True North might have a broader range of potential applications beyond just pattern recognition, for this specific task of real-time MNIST recognition, our NEF system demonstrated superior speed and accuracy with apparently far fewer resources. Another example they compared against is Minotaur. This is an event-based neural network accelerator designed specifically for spiking neural networks, which process information differently. Minotaur achieved an 8% error rate on MNIST, similar to True North, but it was approximately 1,300 times slower than our NEF system. It took 0.152 seconds per digit compared to our 120 microseconds.
1,300 times slower. Wow.
Yeah. And again, memory was identified as a significant bottleneck for Minotaur's design in that comparison. While Minotaur is aimed at implementing different kinds of spiking neural networks, perhaps using event-based sensors, which are also very efficient, for the straightforward MNIST digit recognition task and the pursuit of extreme speed and efficiency, our system's NEF on FPGA design choices proved far more effective in this specific comparison.
What's truly fascinating here, looking across these comparisons, is that while other systems might aim for that absolute peak accuracy at any cost, like the big DNNs, or maybe they aim for broad, general-purpose neuromorphic computing like True North, this NEF system really seems to shine in finding that crucial sweet spot. It achieves high speed, excellent accuracy, good enough for many applications, and absolutely incredible resource efficiency, specifically tailored for real-time pattern recognition. It's not trying to win every single race, perhaps, but it's absolutely winning the efficiency race in a big way for its chosen domain of fast, frugal pattern matching. Okay, so we've explored the impressive present capabilities of this innovative neuromorphic hardware. It's fast, it's efficient, it's scalable. What does the future hold for this kind of real-time, resource-efficient pattern recognition system? Where do the authors see this research going next, and what exciting possibilities could it unlock down the road?
Yeah, the authors highlight several really exciting directions for future work, building directly on their current success. First, naturally, is scaling up. Their design is fully digital and, as we discussed, inherently highly scalable due to its modularity. You can conceptually expand it to handle more complex patterns or much larger datasets than MNest. However, they acknowledge that the main bottleneck for scaling to process significantly more complex patterns, things beyond simple handwritten digits, maybe complex visual scenes or audio signals, will likely be memory bandwidth, getting all the necessary weights and states moved around quickly enough.
Right, memory again, always memory.
Always memory. So future work will need to focus on further reducing memory usage and bandwidth requirements, perhaps by exploring even lower precision weights, maybe going down to just 4-bit, or even purely binary weights and activations, pushing that efficiency envelope even further to fit even more processing power onto a single affordable chip. Second, and this is, I think, a truly transformative goal they mentioned, real-time learning on the chip itself.
Ah, learning on the hardware.
Exactly. Currently, those critical decoding weights are pre-computed offline, typically on a powerful computer using the pseudo-inverse calculation, and then they're loaded onto the FPGA before it runs. A major improvement would be to implement their Opium Light learning algorithm directly on the FPGA hardware.
Opium Light. What's the light part?
Right, this Elite version is a streamlined form of their online pseudo-inverse update method. It's specifically optimized for the much tighter computational and memory constraints you have when implementing something directly on chip in hardware. It's designed to continuously adapt and learn in the field, maybe adjusting to drift or new data patterns, trading just a minimal, maybe 1% performance difference compared to the full offline OPM for the immense benefit of real-time adaptation.
So the system could actually learn while it's running, on the chip, adapting to new patterns or changing environments without needing to be stopped, reprogrammed, or updated from an external computer. Wow. That would truly make it a turnkey solution for dynamic pattern recognition in real-world applications. Imagine a robotic arm on a factory floor that can continuously learn to recognize new types of objects it encounters, or a smart sensor out in the field that adapts to novel environmental anomalies it hasn't seen before.
Exactly. That's the potential power of on-chip learning. And given the reported tiny performance difference between OPM Lite and the full OPM algorithm, about 1% in accuracy, it seems like a very promising and achievable path towards creating systems that have on-chip adaptation. This would enable systems that are not only fast and efficient, but also inherently adaptive and autonomous, much more useful in the real messy world.
Definitely.
They also mentioned they plan to investigate different binarization methods for the input images, since converting grayscale to binary is such a crucial first step in their current pipeline. Any further optimization there, maybe a smarter way to binarize, could potentially enhance accuracy without sacrificing those valuable hardware savings. These kinds of advancements would unlock even more powerful and truly self-contained real-time systems for a vast array of challenging applications.
And that brings us towards the end of our deep dive today. We've journeyed deep into a truly innovative neuromorphic hardware architecture, one that tackles the really tough challenge of real-time pattern recognition with remarkable, almost surprising efficiency. We started with the biologically inspired neural engineering framework, the NEF. Then we moved to its clever implementation on field programmable gate arrays, FPGAs. We explored how ingenious techniques like time multiplexing allow a single physical neuron circuit to simulate thousands of virtual ones. We saw how converting inputs to simple binary values dramatically reduces hardware costs, almost for free in terms of accuracy, and how generating on-the-fly random weights using things like LFSRs saves massive amounts of precious on-chip memory. This system truly demonstrates how intelligent, hardware-driven design choices, where you prioritize efficiency right from the start, can lead to incredibly high performance with minimal physical resources. The real aha moments for me came from understanding the profound impact of those engineering trade-offs they made. The almost negligible performance hit they took from simplifying inputs to binary or using low-precision fixed-point weights. contrasted with the immense hardware, power, and ultimately cost savings. That's a powerful lesson in clever practical engineering.
It really is. It's about understanding what's truly necessary versus what's just nice to have.
Yeah. And the ability to process thousands, potentially even millions of digits per second using less than 6% of a standard FPGA's logic resources. That's truly a testament to this NEF on FPGA approach. It's about getting incredible real-time computational power from very, very little hardware. So thinking about this delicate but powerful balance, they achieved the balance of speed, efficiency, and accuracy. What everyday devices or challenging real-world scenarios come to your mind? Things like smart sensors and remote environmental monitoring systems, maybe, that need to instantly detect anomalies without draining their battery. Or next generation prosthetics that require that split second natural control we talked about. Or maybe even AI embedded right into critical infrastructure, constantly monitoring for structural integrity or security breaches in real time. Where could this kind of ultra fast, ultra efficient, biologically inspired pattern recognition make the biggest difference? Bringing those smart capabilities right to the edge where real time decisions matter most, it really opens up incredible possibilities. What stands out to you as the most impactful application this technology could enable in the near future? Something to ponder until our next deep dive.